Problems for Chapter 10. This is gas laws, very straightforward mostly. So there are a couple of areas that we'll need to look at maybe if you get time on your own, which I'll mention later towards the end of the presentation. So let's go to the next slide. Just to give the credits, most of this is going to be coming from Zumdahl's chemistry with some from Brown and LeMay chemistry. Occasionally some of these sets may have a problem or so from McMurray. And then also from Mr. Max AP chemistry website. Next slide. And the solutions here are provided by myself. Let's go to the next slide. All right, so these are going to be very straightforward, I think, so I'm just going to give you a few general principles. And then when we get towards the end, I'll try to point out a couple of areas that you may want to look at on your own in a little more detail if you have time. So for the problems like the one that we see here in front of us, number one here, the easiest thing for you to do if you're taking a test is to just write out this ideal gas equation. So that's PV equals nRT. So, but I would write it out. It just takes a second, and then you can refer to that as you do these. And let me get my marker going here. Okay, so so number one, assume that you have a cylinder with a movable piston. What would happen to the pressure if you did the following? And the first one tells us that we're going to triple the temperature. So this is going to be before or after, right? Because we're not asked to use 3 of the 4 variables to find the 4th one. We're just told that one thing changes, what would happen to a second thing. So in this case, the ones that are changing are going to be let's see, T and V. All right, so it turns out that you don't actually have to do any math particularly, or actually use any shortcuts here, because we can just look at this equation down here at the bottom, this one, and we can see what's going to happen. So for A, if we triple the temperature, then what would happen to the pressure? Okay, so we're tripling something on this side of the equal sign, and we want to know what would happen to something on this side of the equal sign. Okay, well, it turns out that when you have an equation like this one, whenever you triple something, for example, on one side of the equation, you also would have to triple the thing on the, or something on the other side. Or, you know, you wouldn't have to necessarily do it that way, but the net effect would have to be that way. So in this particular case, if we triple the temperature here, then we'll have to, since the volume can't change because they're telling us up here that we're holding the volume constant, then that means that we would also have to triple the pressure. So for A, the pressure would triple. Okay, for B, if we reduce the amount of gas, in other words this, in, if we decrease that one by 1/3, then what would happen to the pressure? Okay, so again, they're on different sides of the equal sign here. So if we decrease this one by 1/3, we would also have to decrease this one by 1/3. Very straightforward. For part C, decrease V at constant temperature. So here, both of these things, so for this one right here, we're dealing with P and V, and when we multiply P times V, we have to get the same thing in both cases. So, I mean, you could use P1 V1 equals P2 V2 here, but you don't really have to, because what we're seeing here is that we're decreasing V by 45%, which just means that P increases by that same amount, because since they're on the same side of the equal sign, that means if you increase one, then you would have to decrease the other one, right? Because they have to equal the same thing on the right. So if we decrease this one, we have to increase this one, and if we decrease this one by 45%, we have to increase this one by 45%. Another way you could do this one would be to just go ahead and write out some numbers for it, just make up some numbers, and then just see what would happen. So like if you wanted to write the volume as 1 liter and the pressure is 1 atmosphere, then initially you would have 1 times 1, which would be 1. And then if you decrease V by 45%, then figure out what that is, and then divide 1 by whatever you get when you decrease it. So if you start with 1 and you decrease by 45%, you're going to have 0.55, right? Anyway, so, and then when you multiply that by the other thing, you have to get 1. So you can do it any way you want, but I mean, we're not asked to figure out what it is. We're just asked to figure out the general principle. So again, if you decrease this one, you have to increase this one. And then D, have T, which is on the opposite side, and then triple V, which is on the same side as the pressure. So if you have something on the other side, you have to, first of all, you would have to have the pressure on the other side. So first thing we're going to have to multiply by half. So if it was originally 1, it would have to go to 1/2. And then the second part over here where it says triple the volume, if you triple something here on the same side of the equation, you would have to reduce this one by a factor of 3. In other words, you'd have to multiply it by 1/3. So the net effect would be you would have 1/3 of 1/2. So the way that you would figure that out would be just to multiply 1/2 times 1/3. So that would be 1/2 times 1/3 is 1/6. So the pressure would drop to 1/6 what it was originally. Let's go to the next slide. Okay, so I actually did a problem here for part C. And I figured out, so you can look at this if you want to pause the video, and you can see that it turns out the way we said that there's going to be a 45% increase in P. And this is where I actually put in the numbers, but you don't have to do that. All right, next slide. All right, so this is the kind of problem you're likely to see on the exams mostly, and especially on the final, because there's only 3 or 4 questions per chapter. So, I mean, you're almost certain you're gonna see something like this. So when you get a problem like this, it's an ideal gas law problem, but there are 2 kinds or forms. One of them is a stationary form, and one of them is a before-after. So let's read this. Oxygen is sold in steel containers at a pressure of 150 atmospheres. Wow. What V would the gas occupy at a pressure of approximately 1 atmosphere? So notice here they're dropping the pressure dramatically. So you drop it, wow, that's a huge drop from 150 to 1 roughly. T and N are unchanged. This is what kind of a problem? So I asked at the bottom here, is it before or after, or is it a stationary? Well, clearly what's happening here, the pressure's changing, and for part A, the V is going to be changing. And that's it. So, I mean, and actually in the problem statement, that's all we have. That's all we have here, because they're telling us T and N are unchanged. So when you see that, you recognize that this is going to be before after. It's going to be before after. It's not a stationary. So you can use a shortcut, and you don't have to have any particular units except for temperature. So for A, what volume would the gas occupy at a pressure of 102? So if the pressure goes from 150 to 1.02, what would the shortcut be here? It would be P1V1 equals P2V2. And then what you would do is substitute in 49 liters for V1, 150 atmospheres for P1, and then for P2 you would have 1.02 atmospheres. Again, we're doing part A, right? And solve for what? Solve for V2. That's all you have to do. And so that's done on the next slide. And then for part B, what if the temp increases from 20 to 35 degrees C? And P remains constant. So if T increases, what would happen, in other words, to the volume? So remember that your formula for that is V1 over T1 equals V2 over T2, but be careful here because you can't use these numbers here. You have to convert these to K by adding 273 here to both of these. And otherwise, it's just plug and chug. Let's go to the next slide. So for the first one, use P1V1 equals P2V2. Substitute in your numbers here, and your number will be 7,210 liters. For part B, we first convert these temperatures to kelvins. So that actually is going to be 293 to 308. And then use V1 over T1 equals V2 over T2. Or as it's written differently here, it's the same deal. So here it's written as V initial over T initial and so forth. And so you just put in what you know and then solve for your unknown. So again, very, very simple. The thing is it's easier to remember these shortcuts, and if instead of trying to remember all of them separately, you just remember the one main one, which, I mean, it could either be P1 V1 over T1 equals P2 V2 over T2, or if you want to put the N in there too, you would have P1 V1 over N1 T1 equals P2 V2 over N2 V2. Next slide. Okay, so if 15 grams of CO2 gas has V is 0.3 liters, 300 Kelvin, what's its pressure? So this is what kind of a problem? So look at this for a second. Is this a before-after? Well, we don't really have any things that are changing, right? Everything's staying the same. So this must be a stationary problem, which means we want to use PV equals nRT, which means we have to have the units all exactly right. So we want the number of moles in N, rather we want N in number of moles. We want the temperature in kelvins, we want volume in liters, and we want pressure in atmospheres. So what we'll have to do is to substitute in the values that we have here and figure out the pressure, which is the thing that we're trying to find here. So that's our unknown. We're given the temperature, we're given the volume, and we're given the number of moles indirectly here. And then what we'll do is we'll solve for the pressure, but it will be in the units that the ideal gas law spits out, which is going to be in atmospheres. So once we've done that, we'll have to be careful and then make the conversion at the end of the problem to millimeters of mercury, or we'll get it wrong. So the only sticky point here is that we're given CO2 gas in 15 grams. To convert that to the number of moles, divide by 44 grams per mole, which is the molecular mass for CO2. It's about a third. It's about 0.33. And then rearrange PV equals nRT to get P equals nRT over V. So let's go to the next slide. And so we wind up with this. It was actually 0.34 moles when you divided the 15 grams here by the 44 for CO2. And then remember that your R value for these kinds of problems is 0.082. Otherwise, just plug and chug, and you get the pressure in 27.9 atmospheres, but be careful and don't forget, they always answer what they ask, and they didn't ask for atmospheres. They asked for millimeters of mercury. So to convert that, you would multiply by 760, because there are 760 millimeters of mercury in 1 atmosphere. And if you do that, you get the number 21,188, which, since we've only got 2 sig figs here, and for the 300, we're going to just consider that to be infinite. Let's round this one to 2 sig figs. So 21,000. Next slide. All right, I like this problem, and I tend to give it on tests just because of that. It's an interesting problem that you have to think about a little bit. So you might look this over and make sure you're able to do it before the test. The matter in interstellar space consists almost entirely of H atoms at a temp of 100 K and a density of approximately 1 atom per cc. What is the pressure? And then again, they want it in millimeters of mercury. So at first glance, this looks hard, but it actually turns out to be super easy. We just have to make an assumption. And when you have an assumption problem, or what I call a problem where you have to make an assumption, you can make your own assumption. You can choose anything you want, but clearly we have the temperature here, and we're asked for the pressure. But there are 2 other variables, right? The volume and the number of moles. And we only have this little thing here. But it turns out that it's very easy to convert that thing right there to volume and number of moles. How can we do that? Well, first of all, assume a certain volume. And I wouldn't recommend that you use centimeters to the third, but you could. But what I do is I tend to use easy things. So I just chose volume is 1 liter, and that kind of makes everything else fall into place. So now I have my volume, and I just chose it, but that's okay. If they had told me what the volume was, then I'd have to use that, right? But they didn't. So how many atoms would be in 1 liter if you have 1 per cc? Or I guess another way of asking that is how many cc's are in 1 liter? So think back to the beginning of class. We said that there are, we said that a cc, a milliliter, and a centimeter to the third are all the same volume. So we could also ask how many atoms are in 1,000 milliliters. Right, because a milliliter and a cm to the third are the same. And so, in other words, how many milliliters, lowercase m, are in 1 liter? And the answer is easier to see there. Having said that, you should memorize all of them. In other words, there are 1,000 milliliters in a liter, which means there are also 1,000 cc's in a liter. Okay, so we would have 1,000. So in order to get in, we need to use that 1,000. So we would have 1,000 atoms in 1 liter. But we don't want the number of atoms here. We want it in number of moles. So how do you get that? Divide, and I'm not going to write it out because it'll take too long, but divide 1,000 by 6.02 times 10 to the 23rd to get the number of moles. And at that point, you just substitute in these values to the ideal gas equation, and that will spit out a pressure in atmospheres. Again, you want to be sure that you convert that from atmospheres to millimeters of mercury by multiplying by 760. Next slide. Okay, so it turns out that when you do this little conversion here, converting 1,000 atoms to number of moles, you get 1.66 times 10 to the minus 21st moles. And again, your volume would be 1 liter. Use PV equals nRT, and then substitute in the values that we have, where we're going to use 1 liter for the volume, and we're going to use the number that we figured out up there for the number of moles right here. Again, your R value for this kind of a problem will be 0.082, and just figure out what P is. And when you do that, you get an answer in atmospheres, but you don't want that. You want it in mm of Hg, because that's what they asked for up here. So multiply by 760 and you have yourself an answer. Let's go to the next slide. All right, so what kind of a problem is this? So think about that while we read it. Many lab gases are sold in still cylinders with a volume of 43.8 liters. What mass in grams of argon is inside a cylinder whose pressure is 17,180 kilopascals at 20 degrees centigrade? All right, so is this before or after? And what do you think? Well, the answer is no. It is a stationary problem. We can either figure out, or we already have 3 of the 4 variables. So let's look at that. So we have the volume here. We don't have the number of moles, so we'll have to, that's actually what they're asking for. So what we'll have to do, first of all, is figure out the number of moles, and then they don't want it in number of moles, they want it in grams. So we have to multiply it by the gram atomic mass for argon. That's later. And we have the pressure, but it's not in the right units. And we also have the temp, and it's not in the right units either. So for this one right here, we need to add 273. That's easy enough. We'll get 293 Kelvin. This one's a little harder, and this is one of the rare times when you'll be asked to convert pascals to atmospheres. So take a look at that pressure for a second. So what does it mean to say it's 17,180 kilopascals? The reason I'm pausing here for just a moment is because people miss this a lot. So that K stands for 1,000, so that really means there's 17,180,000 pascals. And on the next slide, we'll convert that to atmospheres by using the conversion factor, which is about 101,000 pascals roughly per atmosphere. So just be careful about this K right here, because it's easy to miss it. All right, let's go to the next slide. So the T is going to be 293 Kelvin. The 17,180 kilopascals will turn out to be 1.718, so I've written it in scientific notation, times 10 to the 7th pascals. And then you'll convert that to atmospheres by using this conversion factor right here. 1 atmosphere, 101,325 pascals. So in other words, you're basically just dividing this by 101,325. Anyway, at the end of the day here, we wind up with about 170 atmospheres, which we're now going to plug in right here. And then the volume was given. N's what we're trying to find out. R is 0.082 and T is 293, right? So just solve for N, and then don't stop there. So here's what you get when you do that. But don't stop here, because we were, again, not asked for the number of moles. We were asked for grams. So it turns out the atomic mass for argon is 40, so just multiply by 40, and here is your answer. So, I mean, I think what they're doing in this chapter is they're asking a lot of these in the units that you wouldn't come up with normally, because they're trying to inject a little bit of, like, I don't know what you'd call it, a little bit of suspense into these problems, because otherwise they're very much the same. Let's go to the next slide. Okay, look at this and see what kind of a problem it is. In a typical auto engine, the air-gas mixture in a cylinder is compressed from 1 atmosphere to 9.5 atmospheres, going up about 10 times. And in diesel engines, I mean, this doesn't matter, it's just an aside, but I think it goes up considerably more than that, because one of the deals for diesel engines is that they use the compression to help with the ignition process. But anyway, that doesn't matter. So here we're going from 1 atmosphere to 9.5 atmospheres, and then the volume originally was 410 milliliters. What is this? So is this before, after, or is it stationary? It's before, after, because we have an initial value and a final value, and we're dealing with two things here. Could we have a before, after with three things? And the answer is yes. We could have P, V, and T all changing, and then you would just use P1 V1 over T1 equals P2 V2 over T2. Here, though, we have we're dealing with pressure and volume, so you already know that one by now, hopefully. It's just P1 V1 equals P2 V2, where if you wanted to, you could start with P1 V1 over T1 equals P2 V2 over T2, and then realize that the temp is not changing. They don't even mention the temp here, so just mark it out as not changing. So that reduces to P1 V1 equals P2 V2. P1 is 1, P2 is 9.5, and V1 is 410, and we have to find V2. And notice here, we don't have to change that to liters here, because this is a shortcut. Next slide. So just do what we just mentioned. We're going to get the final volume will be 1 atmosphere times 410 milliliters divided by 9.5 atmospheres. So the key here is just to get it set up. And I've got a little note down here for you if you want to read it. And the answer is 43 milliliters when it's rounded to the correct number of sig figs. Next slide. Okay, so here we're introducing our concept of stoichiometry, which it isn't a big deal. So just kind of follow what I'm saying here. So originally pure O2 gas was prepared by heating HGO. And the equations given, and what volume at STP. So is this before, after stationary? It's stationary. And so we should be given three things, or be able to figure out three things and find the fourth thing. The fourth thing, it turns out, that we need to find out is volume. We are given that it's at STP, that stands for standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 atmosphere. Those are in the correct units, volume's in the correct units. The only thing we need is the N. Okay, that's a little tricky. So they're telling us that we're starting off with 10.57 grams of HGO. So we'll have to figure out the molar mass for HGO, divide how much we have by how much 1 mole weighs. How much do we have? 10.57. How much does 1 mole weigh? I don't have that in front of me, but we'll see it on the next slide. And so anyway, that will give us the number of moles of HGO, mercury oxide. But that's not going to be the same necessarily as the number of moles of what we're interested in. So let's step back for a second. What are we interested in here? Well, the gas, right? So here we've got ourselves a solid, here we've got a liquid. So it must be this thing right here that we're interested in because we're talking about gas laws. So we need the number of moles of gas. So what that means is that since we have a 2 in front of this thing that we just are figuring out the number of moles for, we have an implied 1 here. That means that whatever number of moles we get for this thing right here, we're going to multiply that by 1/2 to get the number of moles of O2. Now this is very straightforward, but it always gives people problems for some reason. So just look at your coefficients. You got a 2 in front of the HGO and you've got a 1 in front of the O2. So for every 2 of the HGOs, you can only make 1 of the O2. So if let's just say we did this and we end up with, let's say 1/5 of a mole of HGO, then we could only make 1/10 of a mole of O2. Okay. All right. So let's go ahead and go to the next slide and look at the answer. So what I'm concerned about here is this part right here. So we have 10.57 grams of HGO, and 1 mole of it would weigh 216.6. To get that 216.6, you add 16, which is the mass of O from the chart, to whatever it is for Hg, which it must be about 200, right? So that's telling us that Hg is pretty heavy. Anyway, when we do this conversion, we get 0.0488 moles of HGO. But again, that's not the number we need. We need half of that, right? Because of our stoichiometry here, the 2 is only going to give 1. So divide that number right there by 2. You get 0.0244. That's something you can do in your head. So here is going to be our number of moles of O2, 0.0244 moles of O2. So we'll just substitute that in for N in the equation PV equals nRT. R will always be 0.82 for this, 0.082 for this one. Temperature, standard temperature is 273, pressure is 1 atmosphere. So just solve that for V. V is nRT over P, and you get 0.5462 liters. Next slide. Hydrogen gas can be prepared by reaction of zinc metal with aqueous HCl. So again, it looks like we've got ourselves a stoichiometry problem. I know that makes you glad. So let's just check and make sure. They give the reaction and they ask us how many liters of H2 would be formed at 742 millimeters of mercury and 15 degrees centigrade if we had 25.5 grams of zinc. So this is going to be a stationary problem. So we'll use PV equals nRT. So we'll need to get all the units in their correct form. So we need pressure in atmospheres and we don't have it. So we're going to have to divide 742 by 760 to get it in atmospheres, and we're going to have to add 273 to 15 here to get the temp in the right units. And let's see, we're supposed to find the volume, and then the other thing we're given is 25.5 grams of zinc, which we have to convert to, first of all, the number of moles of zinc by dividing by the atomic mass for zinc, which we'll do that on the next slide. And then when we do that, though, we're not interested in how many moles of zinc we have, right? So look at the equation. What do we need the number of moles for? Well, there's only one thing there that's a gas, right? And that's H2. And also in the problem statement, they're asking us how many liters of H2 could we make. So now look at the stoichiometry between the zinc here and the H2. It's 1 to 1. So in this case, when we found the number of moles of zinc, we also found the number of moles of H2. Let's go to the next slide. Okay, so zinc here in the middle, zinc has a gram atomic mass of 65.4 grams per mole. How much do we have? 25, roughly 25.5 grams. Divide how much you have by how much 1 mole weighs. So divide 25.5 by 65.4, and when you do that, you get, or you should get, 0.3899 moles of zinc. And then it says here that this will also produce, as we said before, the same number of moles of H2 gas. So here's our N, 0.3899. There we go. Everything else we've already either figured out or we can figure out. 742 divided by 760 turns out to be 0.9763 atmospheres. And I think we're done here. So just substitute in everything except V into your ideal gas law and solve for V, and it will come out in the right units in this case. So it comes out to be 9.4314 liters, which we're going to round down to 9.43 liters, and we're done. Next slide. This is a percentage problem, so again, this is the kind of problem I like to ask. Remember, we've talked about these before, right? Whenever you have a percent problem, I recommend just substitute in or assume better that you have 100 grams. Assume that you have 100 grams total. If you did, how much of that 100 grams would be CO2? Well, it would be 1 gram because it's 1% CO2 by mass. And then once we know how many grams of CO2 we have, we can figure out the number of moles by dividing that 1 gram by 44 grams per mole, which is the molar mass of CO2. 99% O2 means we're going to assume we have 99 grams of O2. And since O2 weighs 32 grams per mole, not 16, 32 because it's O2, not O. So 99 grams is how much we have, divided by 32 grams is how much 1 mole weighs, which is what, about 3, a little over 3. So we have a little over 3 moles of O2. And then we need to figure out the mole fractions for both of these. So let me just finish the problem. What is the partial pressure in atmospheres of each gas at a total pressure? So the total pressure is 0.977 atmospheres. So remember, if you multiply the mole fraction of a gas times the total pressure, you get the pressure for that gas. So let's take these two number of moles and just get a rough ballpark estimate. 1 divided by 44, that's not very much, right? That's just a tiny amount. So, I mean, let's just round it off. 0.02, I mean, that's not really close, but a very small number of moles of CO2. So, but the O2 is easier to see because it's 99 divided by 32. So that one's going to be about 3. So if you add the 3 roughly for O2 to whatever it is for CO2, you're going to get just a little bit more than the 3. So, I mean, most of this mole fraction is going to be in the O2. So when we multiply the mole fraction for the O2, we're going to multiply the number of moles of O2 divided by the total number of moles. Let's go to the next slide. All right, so when we do CO2, I'm looking to see where I did this. Okay, well, it looks like I didn't write it out, but when we divide the 1 gram of CO2 by 44, well, actually, I got it almost right. I can't believe that. So it was 0.0227 moles of CO2. And then again, we get a little bit more than 3 moles of O2. So we're going to add these two things here together to get the total, and then divide the total by each of those in turn to get the mole fractions. So this is just the standard definition for mole fractions. So first of all, we divide the 0.0227. Let me come back up here. by the total, which the total turns out to be about 3.12. So divide that by 3.12, or 3.1165, and then divide this by the same. And here are your mole fractions. For the CO2, it's 0.00728, and for the O2, it's 0.9915. And then just take these two numbers in turn, multiplied by the total pressure, which is 0.977 atmospheres, and that gives you your answer. So when we multiply this number right here times 0.977, we get 0.00711 atmospheres, and that's the first answer, the first part of the answer. And then do the same thing for the O2, and we get 0.969 atmospheres. Next slide. Now, for some reason, this thing is actually actually moving when I click it today. I don't know why, unless I'm living right, because usually I have to click it 4 or 5 times. All right, number 10, an unknown gas, this one's a little tricky, is found to diffuse before through a porous membrane 2.92 times more slowly. So what is the molecular mass of the gas? So this is going to be one of these problems where we have to remember our relationship. That the velocity, for example, before I start going through this, look at the problem statement. Is this gas likely to be more massive than H2 or less? So look at that for a minute. If it's diffusing more slowly, then that means it's bigger, right? Remember, we said that the velocity is indirectly related to, inversely actually related to the mass, but it's not the mass per se, it's the square root of the mass. So this unknown gas here is going to be bigger or more heavier than H2. So you can do this either way. You can put the H2 on top, or you can put the unknown gas on top. And so why don't we just kind of sketch this out? I hate doing this, but let's just write U here. And the reason I hate it is not because I hate writing, it's because it's so awkward and clumsy to write with this thing. But I don't know if we should have not done it this way maybe, but it doesn't really matter. So what would the relationship be on the other side of this equation? And we know the mass of the H2, right? It's 2. So this one right here is 2. And I'm going to have to try to speed this up because I don't want this to get too long. And we don't know what this one is. So that's question mark, which I'm not going to write out. All right, so the velocities over here, the diffusion rates, let's see how I can write this. The diffusion rate here would be about 3 times more slow for the unknown gas. And so on the right hand side, we're going to write a fraction, but we're going to put the diffusion rate for the U thing. I'm trying to remember how this is supposed to work. The reason this is confusing me is because I'm used to doing this for velocities. So the one that goes slower, which one do we want to put that on? Do we want that on the top or the bottom? The rate of diffusion for the top thing will be 1/3. So I'm going to write the 1 on the top and the 2.92 on the bottom. And this is the relationship between the rates of the diffusions for these two things. And so what we're going to have to do is use that thing on the right and we know the H2's mass, but we actually don't want that. So for both of these things, we're going to need the square root. So let me just write that in here real quick. And so we're going to wind up with a relationship where we have a 1 and a 2.92, which I actually did this 2 different ways on the answer. And then we want the square root of the mass of U. So when we find this thing right here, we'll actually find the square root. And then let's go to the next slide and look at the answer. So I did this two different ways. So on the right hand side, what I did was I wrote that 2 over the mass of x equals, and this is going to be the square roots, equals the rate of diffusion of the x thing, which is going to be 1/3 as fast. Okay, so this is the way this should be. So the mass of the H2 over the mass of the unknown gas. So this is what we're trying to find right here. Is going to be the same ratio as the rate of diffusion of the gas, which is going to be 1/3 roughly as much as the rate of diffusion of the hydrogen. So I did it on the left by the 0.3425 here comes from the fact that I divided 1 by 2.92 to get the rate of the unknown gas as compared to the rate of the H. But then over here on the right hand side I did it a different way and you get the same answer where I wrote it as 1 over 2.92. So let's just look at these two things right here. So what this is saying is if you take the mass of the hydrogen over the unknown mass, then that ratio should be the same as 1 over 2.92. In other words, it should be about 1/3 as much. The square root of the mass of the H2 should be about 1/3 as much as the square root of the mass of the X. This one's a little confusing. Anyway, so you can do it either way. So the way I did it over here on the right might be easier for you to see. Anyway, so let's go ahead and do it the way I did it on the right. So we've got, just assuming that you understand how we set this silly thing up. So the square root of the mass of the H2 over the unknown mass equals 1 over 2.92. Okay, so that's what we'd have if we used this thing over here on the right. If we then square that, well, over here on the right, we're going to have 1 divided by 2.92 squared. And over here, from this side, we're just going to get rid of the radical. So we're going to wind up just with the square root, we're going to wind up with 2 over the unknown mass here. And so what is 1 divided by 2.92 squared? Well, it's 0.34 squared. So, that's the way I have it written over here. So let's just switch now back over to this side over here. So we have 0.3425 squared equals 2 over the mass of x. Just take your calculator and square 0.3425. So 0.3425 squared is 0.1173. And that equals 2 over the mass of x. So multiply both sides by mass of x and divide both sides by 0.1173, and you get that the mass of x is 17, roughly 17.05, which rounds to 17.1. Next slide. A particular balloon is designed by its manufacturer to be inflated, and think about what kind of problem this is as we go through it, of no more than 2.5 liters, which that is not a value that we're going to use at the beginning to figure this out. That's something we'll check back on later in the problem. So for right now, you don't have to worry about the 2.5 liters. If the balloon is filled with 2 liters, so the initial volume is 2 liters, and it's released and rises to an altitude at which the atmospheric pressure is only 500 millimeters of mercury, will the balloon burst? So is this before or after, or is it stationary? And the answer is it's before or after, clearly, right? The initial volume would be 2 liters, and the final volume is what we're trying to figure out. And the initial pressure is what? Does it say? Well, it doesn't directly, but if it's at sea level, it's going to be 1 atmosphere. How many millimeters of mercury is 1 atmosphere? 760. And then this final pressure will be 500 millimeters of mercury. Okay, so this is a before-after, and these are not temperatures we're dealing with here, so we can actually use the units that they gave us here. we're trying to find the final volume. So the initial volume is 2 liters, the initial pressure is 1 atmosphere, and the final pressure would be 500 millimeters of mercury, or if you wanted it in atmospheres, you would divide 500 by 760. You can leave this in millimeters of mercury if you want to, it doesn't matter, or you can convert it to atmospheres. You'll get the same answer because it's the ratios that we care about. And for the liters, you might as well just leave it, right? Let's go to the answer then. So we can use P1V1 equals P2V2, and we know everything except V2. So rearrange to get V2 is P1V1 over P2, and then just substitute in the values. Now when I did it here the first time, I put in atmospheres for the pressure, but you don't have to do that. As I said before, you can just go ahead and divide in terms of millimeters of mercury, because you're going to get the same answer. So if you did it this way, for this one over here, you would have to change 1 atmosphere to 760 millimeters of mercury. You get the same answer. And when you do this, you wind up that V2, the final volume, is 3.04 liters. Now, it's at this point that we want to look back to what they said at the very beginning. 2.5 liters is its maximum capacity. So that means if it goes up to 3 liters, it's too much. So it's going to cause the balloon to burst. Next slide. Consider the following reactions. 4Al plus 3O2 gives 2Al2O3. It takes 2 liters of pure oxygen at STP to react completely with a certain sample of aluminum. What is the mass of aluminum reacted? Okay, you can look at this hopefully now fairly quickly and determine this is a stationary problem. And we are given the volume in liters here, 2 liters, and we're given that it is at STP. So that means we're at 273 Kelvin and at 1 atmosphere. And we're supposed to find the mass of aluminum. To do that, we have to find the number of moles of aluminum. So what we'll have to do here is use what we have to try to figure out the mass. So for this one, again, we're dealing with gases in this chapter, and only one of those things that we see there is a gas, right? And that's O2. And so what is the mass of aluminum reacted? So let's set this up before we go to the next slide. We have the temperature, we have the pressure, we have the volume. So what we can do is find the number of moles of O2. Why O2? Because that's the only thing in here that's a gas. So it doesn't really mention O2 in here. It actually asks for aluminum, but we know that it's going to be the O2 because the aluminum is not a gas, obviously. So what we'll have to do for this problem is we'll have to find the number of moles, first of all, for the O2. So we know, and it is mentioned here, I didn't see that. So 2 liters of pure O2 gas at STP. So those things will allow us to find the number of moles of N, but that's going to be for the O2, not for the aluminum, but they're asking for the aluminum indirectly. So what we're going to have to do here is we're going to have to find, first of all, the number of moles of O2 by using the ideal gas law. And then once we've done that, we're going to use the stoichiometry again, which is 4 to 3. So for every 3 of the O2s that we have, we'll use 4 of the aluminums. So whenever we get the number of moles of O2, what we're going to have to do is multiply that by 4 over 3. And then we still aren't finished because we have to then multiply by the mass of aluminum, the atomic mass. So let's go to the next slide. So first of all, we're going to solve for the number of moles of O2 by plugging in everything else from the problem statement. And when we do that, we see that the number of moles of O2 is 0.08934, which we then want to multiply by 4/3 to get the number of moles of the aluminum. So when we multiply 4/3 times this number right here, we get 0.11912 moles of aluminum, and then we multiply that by the gram atomic mass for aluminum, which is 27, and that's done here. So multiply 0.11912 moles times 27, and you get about 3.2 grams of aluminum, which I've rounded over here on the right to 3.22 grams of aluminum. Next slide. If the density of water is 1 gram per milliliter and the density of mercury is 13.6 grams per milliliter, what this is basically telling us is that mercury is about 13.6 times more dense than water. How high a column of water in meters can be supported by atmospheric pressure? So atmospheric pressure is 760 millimeters of mercury, and that is about 76 centimeters, so it's about 3/4 of a meter, because there's 100 centimeters in a meter, right? So in English units, that's about 3/4 of a, kind of like 3/4 of a yard. So anyway, that would give you an idea of how high this would be. For water, if we wanted to put water into a barometer instead of mercury, it would have to be much higher. Right, so how would we figure out how much higher it would have to be? Well, if mercury has to be 760 millimeters high, then can you figure out from the problem statement how we could figure out the height the water would have to be? Well, if mercury is 13.6 times as dense as water, then we would have to multiply this 760 here by 13.6. Okay, so we would have to multiply that by 13.6, which I'll just do in my head to give you a ballpark estimate, and then we'll look at the answer. So it would be 7,600, and then about would be 20. So that's right around 10,000 millimeters. So if we multiply 760 here times 13.6, we're going to get about 10,000 millimeters, but we want the answer to be in meters. So again, we'll look at this in just a second, but so that would be about 10 meters. Let's go ahead and go to the answer. And so I didn't actually write out what the number was. So anyway, so the reason that you multiply by 13.6 here is because of the density difference. So because mercury is much more dense than water, it's much more compact. If you wanted to replace the mercury with water, you'd need to have 13.6 times as much water as you do the mercury. So anyway, you just multiply 13.6 times 760, and then you would get an answer in millimeters of water, but we don't want that. And the reason we don't want that isn't because it isn't the right answer, it's because they asked for the answer in meters here. So to get that, just divide by 1,000 millimeters per meter, and you get 10.3 meters, and that is answer choice D. Okay, so the key here for this problem is to understand why we're multiplying here by 13.6. Let's go to the next slide. The ideal gas equation, this is multiple choice. These are some of the questions that I wrote myself the first semester I taught, just to give people a chance to see what these are like. The ideal gas equation correctly describes the relationship 1 for a real gas between pressure, temperature, and volume. So what you're supposed to do for these multiple choices is you're supposed to go through first the 4 answer choices that are directly below the question, and see which ones of those are correct, and then come down to the bottom and answer the question. So what I usually do is I go through each one and put either a check or an X next to it. And so I'm going to put an X next to 1 here because it's wrong, because it doesn't correctly describe the relationship for a real gas. It describes the relationship for an ideal gas. So that is X. Number 2 can be written PV equals nRT. The ideal gas equation can be written PV equals nRT, and that is correct. Number 3, the standard molar volume is 24.4 liters. Is that right? So think about it. Remember when we did the standard molar volume, it was 22.4 liters, not 24.4, right? So this is not right. So this is going to get an X. And then number 4 can be adapted by the addition of 2 correction factors to describe real gases, and that is correct. We call that the van der Waals equation, and that is one of the topics that we studied in this chapter. And it tells us that if we add the A and the B factors to the pressure and the volume, that will adapt it to make it so that if you look up the A and the B value for a particular gas, you substitute those in, and you also have to know the volume and the number of moles, then you can actually adapt this to the ideal gas. So anyway, that one's correct. So 2 and 4 are correct, so the answer is going to be E, 2 and 4 only. Next slide. And here's your answer. Next slide. The partial pressure of a gas. The partial pressure of a gas, 1, can be written as the gas's mole fraction divided by the total pressure. So here's a little tricky word here. Is that right? And the answer is no. It's not divided by, it's multiplied by. So answer choice 1 is going to get an X. Number 2, when summed with the partial pressures of all gases in the system, will equal the total volume of the system. Take a look at that for a second. When summed with the partial pressures of all gases will equal the total volume. How can you get a total volume? By adding up pressures. So this one is wrong. If the word volume here were changed out and replaced with pressure, then that would be correct. Number 3 will never equal the total pressure of the system. Okay, so for this one, the answer is that it could equal the total pressure of the system if there's only one gas. So like if you've got a balloon with O2 in it, then the partial pressure of the O2 gas will equal the total pressure of the balloon, because the mole fraction for the O2 would be 1, right? So you would multiply 1 times the total pressure. So the way this is written, this one is also wrong. So we've only got one chance left. 4 can vary from less than 1 torr to 760 torr if the total pressure is 760, and that's correct because it could be any of those numbers. It could be anywhere between 760 and just above 0, right? I mean, if you just had like just a little bit of it, you might have 0.1 torr or something like that. So 4 is correct, so let's put a check by it, and the answer is going to be D, 4 only. Next slide. Next slide. According to the kinetic molecular theory of gases, remember this is what we talked about when we talked about the velocities and all of this, pressure is proportional to volume. 1. No, pressure is indirectly proportional to volume. 2, the average speed of a helium atom is less than that of an H2 molecule. That is correct, because helium is heavier than H2. H2 has a mass of 2. Helium has a mass of 4. It has 2 protons, but it also has 2 neutrons. So because helium is more massive than H2, it will move more slowly. So that answer choice is right. 3, an increase in temperature will produce a decrease in the volume. So, I mean, if you think of it in terms of the ideal gas equation, T and V are on opposite sides of the equal sign, so if you increase one, you have to increase the other one, assuming everything else stays the same. Or just from a common sense viewpoint, if you have a balloon and somehow you can heat the air in that balloon up, then, I think it's just common sense that the volume is going to increase, not decrease. So we're going to mark X by number 3 and go on to 4. And the average speed of a gaseous atom or molecule is indirectly proportional to the square root of its mass, and that's exactly right. So the bigger it is, the slower it goes, so we call that indirectly proportional. But it isn't indirectly proportional to the mass, it's indirectly proportional to the square root of the mass, so that's absolutely right. So 2 is right and 4 is right, so the answer is going to be D, 2, and 4. Next slide. Next, the behavior of real gases, 1, can be described by the ideal gas equation if corrections are made for the intermolecular attractions in molecular volume. That's absolutely correct. So that's just exactly what we said when we talked about this in that section. In most cases, too, we'll show a large deviation from the ideal gas law. This shows us that the ideal gas law is basically useless. No, that's just nonsense, right? Because if it were useless, we wouldn't be talking about it. 3 is described fairly accurately by the van der Waals equation. Yeah. 4 can be correctly described by simply using the ideal gas equation. No, because if that were the case, we wouldn't have needed to go through all that derivation for the van der Waals equation. So it looks like we've got 1 and 3 here, and that is answer choice A. Next slide. Next slide. A flexible vessel is filled to a certain pressure with 34 liters of gas under conditions of constant temp and moles of gas. How does the pressure change? If we decrease the volume by a factor of 4. So remember, the P and the V are going to go in opposite directions. So if we decrease the volume, we're going to have to increase the pressure by the same amount. So if we decrease the volume by 4, we increase the pressure by 4. So answer choice D looks like the correct answer here. Next slide. All right, so that brings us to the end. All right, so we only have one more chapter to go. So just if you have time, I want to wrap this up, but if you have time, you might try to find some more problems, because I don't have them in here, but just to strengthen your ability to work on, like, for example, the problem that we did as far as finding the relative velocities according to their masses. So you might check Mr. Mack's website on this chapter, the gas chapter. And you might also, I didn't put one in here really, not directly, but if you have time, you might just check to see if you can find a problem either in the textbook or online that deals with that van der Waals equation, where they actually, like, say, okay, here's A, here's B, figure out what, pressure, or figure out what temperature or whatever would be. I don't think you're likely to see that either on my test or on the final, but anyway, just in case. So let's call it a day, and I'll see you in chapter 11.